Okay, welcome everyone. In this video, I want to talk about how we can define matrix multiplication both in general and then how we can perform that operation in R. So let's consider two matrices to motivate this example. Matrix A is a 2 by 3 matrix, first row 1, 2, 3, second row 4, 5, 6. And matrix B is a 3 by 2 matrix. It has 3 rows and 2 columns. The first row is 1, 4. The second row is 2, 5. The third row is 3, 6. So the first thing I want to just emphasize, just like addition, it's not possible to multiply any two matrices. So matrices A and B, their sizes need to satisfy certain conditions in order for the product of two matrices to be defined. And it's different than addition. So we can multiply matrix A and matrix B. These two matrices have different sizes, right? And we're going to still be able to multiply them together. So the way that we define matrix multiplication might seem not so intuitive to you if you've never done this before. So what we can do is, let's say I want to define this product. I'm going to call it AB. Okay, we're going to multiply matrix A and matrix B. I'm going to get some matrix that is a result. So the first thing is, well, what goes like in the first position in that result? So what is the entry in row 1, column 1? And that's what this is referring to. So to figure out what goes first in my product, what the first entry in row 1 is going to be is I take the first row of matrix A and I take the first column of matrix B. So I take row 1 over here. I take column 1 over here. And I'm going to do something with these values to figure out what goes in position 1, 1. And what I do is I'm going to multiply these two vectors together and then take the sum of them component wise. So I'm going to take 1 times 1, and that comes over here. Then I take the next two values and multiply those together. So then I take 2, in this case times 2, and that goes over here. And then I take the last entry of row 1 in A, the last entry in column 1 of B, that happens to be 3 times 3. So I take row 1 of the first matrix, column 1 of the second matrix, and I multiply the elements pairwise and then add them together. So in this case, I would take 1 times 1 plus 2 times 2 plus 3 times 3, and that gives me a value of 14. And that's what I put right over here in this first place. Let me clear out my question mark. And over there, instead, drawing with my finger, so bear with me, goes 14. Then if I want to figure out what goes into position, the next position in the matrix, which is in row 1, column 2, I take row 1 of A, but now I come over to the matrix B, and since I want to figure out the position in column 2, I take column 2. So now I would take these two vectors, I multiply them pairwise. So I would take the 1 times the 4, and then I would take the 2 times the 5, and the 2 comes from this as the second entry over here. The 5 is the second entry over there. And then I take the last entry, multiply the two last entries, which is a 3 and a 6. So I have these three products. I add them all together, and I believe that gives me 32 in this case. So that's what goes over here. Okay, then next would be, that takes care of row 1 of the product, and then I would go into row 2 of the product. So for that, next I would take row 2 over here of matrix A, and I would multiply that by column 1 of matrix B, and that's going to tell me what goes in the 2, 1 position in the result. So I would take 4 times 1, which is 4. I would take 5 times 2, which is 10. And then I would take 6 times 3, which is 18. Add those all up. So that is like 28 plus 4. I think that gives me 22 over here. And then finally, I have one more entry over here that I could find in the product. And that entry I would get by taking row 2 of matrix A, column 2 of matrix B, and then doing a similar product of 4 times 4 plus 5 times 5 plus 6 times 6. And so let me clear out my drawings and show you summarize it down below over here. So this is what I've summarized in this last matrix again, that this value right here came from taking this row times this column. And this over here, it came from taking that first row of matrix A and multiplying it by the second column over there. And we just went through this term by term. So hopefully the way I've organized this makes sense. This is that last value that we got by taking this row 2 of matrix A, column 2 of matrix B, 4 times 4 plus 5 times 5 plus 6 times 6, and that gave us 77. I think I had 22 written up top. This was a 32, sorry. So the result here is I take matrix A, which has 2 rows and 3 columns. So this is a 2 by 3 matrix. And it made sense to take that matrix and multiply it by matrix B, which had 3 columns, 3 rows and 2 columns. And when we took that product, the result, AB, notice, was a 2 by 2 matrix. It had 2 rows and 2 columns. So we see some interesting things come out about what the sizes of matrix A and B need to be in order for the product to be defined. So one thing that we see is that this product is defined only if the number of columns of A, which in our case was 3, A had 1, 2, 3 columns, is equal to the number of rows of the second matrix B. And so matrix B had 3 rows. So that was able to match up because we need to have the same number of things in each row of matrix A as we have the number of things in columns of matrix B. So these two matrices, the product of two matrices, again, is only going to be defined if the number of columns of the first matrix equals the number of rows of the second matrix. And moreover, the size that we get in the end, we can figure out by looking at how many rows did the first matrix have and how many columns did the second matrix have. So when I take a 2 by 3 matrix and multiply it, in this case, by a 3 by 2 matrix, that results in a 2 by 2 matrix. And so we could generalize this to matrices of any size. And if I take a matrix which is M by N, so it has M rows and N columns, then the product is only going to be defined if my second matrix B also has the same number of rows, N, as matrix A had columns. So I can take an M by N matrix A, multiply it on the right by an n times p matrix B, and the resulting product AB will have size m rows and p columns. So in the end, the product is going to have size m by p. So this is a really important and maybe slightly complicated thing if you haven't multiplied matrices before, in that the size of the matrices, in order for the product to be defined, that condition is a little bit more complicated, and that is the number of columns of the first matrix needs to equal the number of rows of the second matrix. So two matrices that have the same size cannot necessarily be multiplied together. So I think addition and subtraction of matrices is much more intuitive than the way that we define matrix multiplication. But that's how we can define matrix, the multiplication of two matrices. And the next thing would be, well, how can we do that in R? And so to multiply two matrices in R, we don't use the regular multiplication symbol. Instead, we need to use this operator, which has percent sign, then asterisk, and then percent sign. So this is what we mean by matrix multiplication. Okay, so we'll practice an example in the next video.